This video is Lab 3 for Physics 2211, Section N on finding the mass of a black hole. In this lab, I'll use the given trajectory of a star revolving around a black hole to find the mass of the black hole, assuming the only force on the sun is the gravitational force of the black hole. Newton's second law, which is the net force equals the change in momentum over the change in time, or the net force equals mass times acceleration, can explain how we will calculate the forces on the star being only the gravitational force of the black hole. With Newton's second law, we can split the net force into the parallel and perpendicular forces, which can be calculated using these values in terms of momentum, which are dp dt would equal the d of the magnitude of p over dt times the p hat plus the dp hat over dt times the p magnitude. Along with Newton's second law, we will use the universal law of gravitation, which is the negative g constant times the mass of one object times the mass of the second object over the distance squared, the magnitude of distance squared times the r hat. To finally evaluate to calculate the mass of the black hole, since the only force on the star is the gravitational force of the black hole.
In order to solve for the base of the black hole mass, we will create a computational model to implement changes to create both a representation of the star's trajectory and to calculate the magnitude of the forces on the sun and the mass of the black hole. At the start of the code, we need to set g, the constant, equal to 6.7 times 10 to the negative 11th, the star's mass to 2.0 times 10 to the 30th kilograms, and the change in time to 1 day, which is 86,400 seconds. In the loop, we'll set the initial momentum to the star's mass times the initial velocity, and the final momentum to the star's mass times the final velocity. The change in velocity will be the final velocity minus initial velocity, and the change in momentum will be the final momentum minus the initial momentum. And then dp dt will be the change in momentum over the change in time. Then we set the net force equal to dp dt. And for dp dt parallel, we set the p hat equal to the initial momentum over the magnitude of the initial momentum, the d magnitude p dt equal to the magnitude of the final momentum minus the magnitude of the initial momentum over the change in time, and the dp dt parallel equal to the d magnitude p dt times the p hat. Then we set the f net parallel to dp dt parallel. Then we set dp dt perpendicular to dp dt minus the dp dt parallel, and the f net perpendicular will equal dp dt perpendicular. To calculate the mass of the black hole, we will create a distance vector, which is from the origin, where the black hole is located, to the star's position. With this, we use the gravitational law to set the mass of the black hole equal to net force times the magnitude of the distance squared over the g constant times the star's mass. Finally, to represent the forces as arrows, we create 3 arrows, each positioned at the star's position. And we set 1 arrow to the net force, 1 arrow to the parallel net force, and 1 to the perpendicular net force. And we set the arrow scale to 1 times 10 to the negative 17th to be able to see the forces as arrows. After running the code with the changes implemented, we can see in this video the trajectory of the star around the black hole, as well as the arrows representing the net force parallel, and the net force perpendicular as the star moves in the trajectory. And the results we get is the net force to be 8.923 times 10 to the 28th newtons, parallel force to be 1.120 times 10 to the 28th newtons, the net force perpendicular to be 8.859 times 10 to the 28th newtons, and the black hole's mass to average out to be about 1.37 times 10 to the 34th kilograms. After completing the lab, we need to clarify a few questions. First, how are the net force and its parallel and perpendicular components different from the rate of change in momentum and its parallel and perpendicular components? Now, the force and dp dt are numerically the same, but the force cannot be measured. So in this case, where we have the star revolving around the black hole, we have the velocity as well as its mass. So we use dp dt, which we can measure, to determine the force, because the two are numerically the same. Next, if the motion of the star was unchanged and a new black hole was placed in the old black hole's position, and still the only force is gravity of the black hole acting on the star, could you tell the difference between the two black holes? Since we use the trajectory and the universal law of gravitation to determine the black hole's mass, we would not be able to determine a difference between the new and old black hole's mass because the information we use to determine the old black hole's mass is the same, and therefore in determining the new black hole's mass, it will be the same as the old black hole's mass. Thank you.